Word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for these students, and I just pray you'd help us use this time wisely to prepare for the third test in this course, Lord. Amen. All right, so you guys got questions in particular?
The way that we proved ideals in this book compared to the way that you've done it last year, it seems that you had, like, you take an element in the ideal A, two elements in the ideal A, and show
No.
the difference is still in there.
Yeah.
They don't do that in our text, or I haven't seen it. Is that something you want us to do?
The subrating test.
No, specifically for, like, the definition of an ideal. I'm pretty sure in your notes it said, like, if A and B.
Yeah, I think in the book they just say that an ideal has to be like a sub-rung.
Yeah.
And so I think in his notes he proves that it's a sub-rung first and then an ideal.
So,
But each one on the test,
yeah,
like,
like
you
when-
ask, like, show this is an ideal.
Because in, like, our book, when they show that something's an ideal, they just say little a, big R is a subset of big A, and big R, little a is a subset of big A. But then, yes, so we skip that I.
well, you know, I just opened the notes. It's already here. It's kind of funny. Yeah. That's, yeah.
That's exactly what I'm talking about.
Let's see here. Non-empty subset A of a ring R is an ideal if whenever A and B are in A, then the difference is in A, and we have multiplication from anything in the ring times things in A are again in A once more. So ask your question. What was your question again?
So on page, in our text, it seems that there, on 181 it says, limited subgroup A of the ring R is called an ideal. If-
Whoa. Page what?
181. It just seems that they care about the second condition. In any of their examples, I've never seen them show the first one.
Well, I mean, it's right there. I mean, an additive subgroup A.
Right, so that's why.
Yeah, I mean, proving that whenever A and B are in A, that A minus B is in A. I think that establishes that A is a, well, I think I need more actually, right? I mean, I need, but you notice even mine's got fine print too, right? You notice what the fine print is on mine?
Does zero have to be in there?
No? Well, we usually check, why do we check zeros? Like back in linear algebra, why do we check if zero's in the subspace?
It's not empty.
It's just it's not empty. It's, so that's also here. My laser, I left it in my office. Sadness. I have to go to a more low-tech laser. Let's see here. But yeah, non-empty is right there. So there, you know, if I just said a subset A, then I'd have to add a third condition, which is that I could add the third condition 0 be in there because I know that's in there, but any element would do to prove it's non-empty. So in the same spirit, Nicholson on page 181, he has rolled condition 1 into the little wordplay an additive subgroup A. So his additive subgroup is, but you know, it depends on the example. Is there something to show or not? A lot of times there is. But other question? Yeah, he never really, and I guess that's kind of, you know, he never actually has a standalone theorem about testing whether something's an ideal, right?
Yeah, that's why I thought that was the only way to go about it. But if we're not given that it's an additive subgroup, I just have to show that
Right.
the difference is
So his ideal test is kind of, it's, you know, it's wording here and then reference to a additive subgroup test way earlier in the book.
If something's going to be, because I know there's people who really start to assume that the ring is commutative, will you tell us explicitly on the test whether something's a commutative ring or not?
Yeah, you should assume that they're not commutative unless otherwise stated, yeah.
But where's
On the other hand, you should also assume that there's a decent chance I would forget to say it's commutative when I intend it to be.
So ask.
So you should ask if confused, yeah.
And also we're saying like ring has identity.
Yes, a ring for us has identity. If I talk about an RNG, that's a ring without, or a general ring in the language of Nicholson. And I guess one of the things that occurred to me was, I think when I wrote the first, I mean, so you guys on mission 10, right, mission 10, the first problem on mission 10, didn't it feel, it felt off, right?
Yeah. Oh, yeah. We asked Jess about it, and we determined that we were going to email you, but we were doing it embarrassingly. That email
Yeah. Yeah, it's
You're trying to
okay.
subtract
I gotcha. But, you know, I mean, Kang asked me about this way behind. I hadn't had time to re-image this problem into something interesting. But, you know, I do have a test. And what I'm trying to get at here is there must exist other formulas that I could give between 2x2 integer matrices and the integers, which would actually produce interesting kernels and make the rest of this problem, you know, not as kind of stupid.
I like this problem. You can pull it like this on the test, like
Exactly this, yes.
Or like A12 minus A21, just flip it a little bit, change it up.
You said I can change it. I can.
That's what you were trying to write.
Oh, I can change it to A22 minus A11 instead.
Yeah.
Yeah.
You were trying to do A11 minus A12, right?
I might have been meaning to put plus there and see what happens.
Don't do that.
I don't know. I have to think about this. I feel
We did it.
I've forgotten what the source of this problem was. I feel like there exists a more interesting version of this that I tried to change a little bit and changed poorly, but I can't remember where I found it. So
You had a similar one last year in your.
really?
Yeah, it was from Galleon. I actually found the
But it
original
actually
problem
wasn't
was in Galleon.
Okay, which
A minus B.
number was it? Do you know?
I wrote it down on the mission, but I don't have the mission with me. It's like either one, no, it wasn't 125, it wasn't 119.
I'll look in the group. Yeah.
119?
Yeah, give me the group meeting. We scroll far.
Yeah, I looked.
We can find it.
I looked the problem up in Galleon's
Like 117
textbook.
or.
That should be around like lecture 26.
No, I found the textbook online to look it up.
No, that's not it. Lecture maybe 28 then.
It was still a different problem, but they asked for A11 minus A12 or something like that.
That's what we ended up just doing.
Yeah.
It was actually a mistake.
Lecture 27 maybe?
No, it's still like a hard problem. It's the
Probably the first one.
I'm gonna guess 107.
107? I think I was looking at.
There it is.
Yeah.
Oh, yeah, there it is.
Yeah.
Oh, you see what I did?
You're
Yeah,
trying to do like A12.
I should have done A11 minus A12. Hey, which is what Kang told me to change it to. Oh well, I didn't listen. I should have listened to him. What's that?
That's what Devin and I did.
Ah.
I found it in Galleon, and I was like, oh, I guess it was too late to email you.
Ah, but yeah, this is obviously
It was more interesting.
it's a more more interesting problem. Of course, now that we've talked about it, it won't be on the test. But
Or is that you just trying to trick
He's
us?
trying to throw us off.
or yeah, that's right. It might try to throw you off the trail. I mean, I don't know. We can't know these things, right? I mean, I'm sorry. I have too much fun. Let's see here. Yeah, this one's actually the kernel's actually non-trivial. The image is clearly the whole integers. So R mod the kernel is the integers, which is kind of interesting. That would be a prime ideal because the image is an integral domain, right? So the quotient is producing an integral domain. Consequently, it's an ideal. But it's not maximal because that's not a field. Z is not a field. So apparently, kernel phi is not a maximal ideal. Yeah. Here's a question. If kernel phi is not a maximal ideal, so what does kernel phi look like? AAAA, right? So I guess my question for you guys would be, So this is allegedly not a maximal ideal. Can you tell me what is bigger than this? But not the whole 2x2 ring of integer matrices? Wait a minute. I'm sorry, the ring is what? It's not, that's wrong. What's the ring? Yeah, it's these A, B, B, A. I mean, apparently, if the theory is correct, or, well, I mean, is this but by the way, is this a commutative ring? I don't think we know that theorem for non-commutative rings, do we? No. So are we out of bounds here, by the way? See, I don't think we are, because I think, well, 2x2 matrices generally don't commute. These do. Because essentially, this is isomorphic to A plus bj with j squared being equal to 1. And those commute. You can prove this is a commutative ring despite its non-commutative origins. So my question remains, can you think of what ideal would that J look like? I mean, if that's not maximal, there must exist an ideal between kernel phi and R. What is it? I don't know right offhand. And yet, it's not a field, so there must be something out there. What is it, though? Interesting. Curious.
It seems like the only other thing you could do is fix one of that diagonals.
Yeah, I guess we could look at it. I mean, what is that? What would we need? We'd need J would be things like what? But yeah, if it's
1A.
oh, but this is a subset. What's that again?
1A, A1, but I don't think that's big.
1A1.
Yeah. But that's the only thing I was thinking that you could do. Well, if A is 1, then it's in there, but then
I don't know. Huh. I mean, whatever we put, if this is a typical element of J, right? It has to allow the possibility of this, but it doesn't have to be that either, right? I mean, so we can't put ones here because that forces A to be 1. Well, that would mean it's not getting. I mean, there are things in here that might not be.
it's not getting everything.
Yeah, I don't think it would. But we're stuck with it being a subset of R as well, right? So we do have that things in J look like A, B, A, B, B, A, B, 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 A. And we had some theorem about remember we studied some theorems early on about the interplay between ideals of a ring and ideals of the matrix ring over that. right? What was that theorem that we? I don't remember. That might be helpful here. I think it was in the ideals section, right?
On page 185, we have maybe 184.
Ah. But also be careful here. We're not actually looking at a matrix ring, are we?
Oh, no.
I mean, this is a ring of matrices, but it's not a matrix. A matrix ring is Z2 by 2. Right? So like, if we were looking at Z2 by 2, then this theorem is helpful to us because it would say that the only ideals of Z2 by 2 are what? They're things like NZ 2 by 2. Because what are the ideals of n? Well, just nz. That all ideals of the integers have the form principal ideal generated by n. And so that theorem on page 185 would tell us about the structure of ideals of the matrix ring. But annoyingly, this is not a matrix ring, although it is a ring of matrices. You got to understand, matrix ring is just the full set of matrices over the ring. Yeah. I know this from personal experience that this terminology is frustrating because when you first hear matrix ring, you think it's sort of a generic label for rings of matrices. No, it's a specific ring. It's the set of all matrices over the ring.
Like, would R be a subring of Z2 by 2?
No. I don't think so because it's not of the form. Is it of the form NZ 2 by 2? So I don't think that's an ideal of Z2 by 2. Oh, subring. Is it a subring? Yeah. I think that's fair. It's got the identity, the sum, the product, difference. It's all in there. Yeah. Yes. You say we could have a whole test on subrings?
Well, no, I'm just saying, like.
We could have a whole test on
We
subring.
could, that would be great. We knew ahead of time.
We knew exactly what.
Uh-huh. Yes, I wouldn't want to inconvenience you with learning something you didn't need to learn, I know. But I don't know. How would you attack that question? I mean, you're.
Put it on a test file, just try to see.
Put on a test and like put people's names next to it if you want to figure it out, and then the rest of us can. Just give us all the points.
Nobody
and
gets
then
your
we
credit
just
when they
get
get
it.
20 points that don't factor into 30 rest of the score.
I don't know. I gotta look at this one more later. I'm gonna stop fiddling around with it at the moment. By the way, that does not mean it's too hard. It just means I don't see at the moment what to say more about it. Anyway, you guys have other questions? That wasn't actually your question. It was just me blathering. We left your question a while ago, I think.
What exactly should we know about like the delta function? Like all we really know is like delta of A B is greater than or equal to delta of A.
Let's see.
That's like the only solid thing.
Yeah.
Oh yeah, if it's a unit, the delta of a unit is 1. But like,
Is that actually said? Is that del-
If
Is it a
you use a
Euclidean
unit, delta of u equals delta of 1.
it might be-
But she said it was equal to 1.
No. It says
No, I said delta of 1.
It says
Oh, did you?
No, I said 1. I meant the.
But yes, that much we can prove. In fact, we've talked about that in the other help session that the divisor function of any unit is going to be the same as the divisor function of 1, whatever that happens to be. Yeah, right. I mean, so where's that pesky definition? 270 what? 270. I mean, I guess I mean, here it is. I mean,
Yeah, are those like just the only solid things you really know about it?
and the exercises.
Okay.
Yeah.
Yes, theorems.
It was like 19.
Yeah, 1920 and 21 we all use all those.
So, I mean, there is more than I can say. Delta, and we've figured out that it is supposed to go from R, despite, depending on,
Which version you have?
exactly. And keep in mind that this n has 0 in it. Because it's his n, it's not my n,
It's a fake.
Yeah. The internet war on that rages on to this day. Satisfies, what was it? I lost my place. Oh, the division algorithm. And if A is not equal to 0 and B is not equal to 0, we get that delta of AB is greater than or equal to delta of A. I mean, it's fine, I suppose. And you guys know what division algorithm means here. Should I write that down? Yeah, so to say satisfies division algorithm means for each P in R, there exists Q and R in R such that P equals to, for each, I need a D too, right? There exists Q and R in such that P is equal to QD plus the remainder, right? Where either the remainder is 0 or the divisor function of the remainder is less than the divisor function of D. That's the division algorithm. Now, yeah, perhaps it's useful to collect what we learned in the exercises about this thing, right? Because I agree with you that the actual definition is awkward. But it turns out this silly business about the less than or equal to this pesky, I mean, it took us the better part of 20 minutes to kind of demystify that as it relates to these exercises. But after the dust settled, what did we learn? So yeah, fun facts. Let's see here. For Euclidean domain?
Yeah. A associates B implies delta of A is equal to delta of B.
All right. Is that if and only if?
No.
All
Some
right.
directions you also need that A divides B.
So if
If
A divides B and,
delta B,
all right.
then you have versus.
And I feel like this is the place we were warned that we need B non-zero.
Right.
What else was there?
Yeah, the next one, B is a non-unit if and only.
Which number is that?
21.
21. B is a non-unit if and only if.
Delta of A is greater than delta of A. So I guess
And is that for all A? I mean, which A?
For all A not equal to 0. I guess you could also flip that and say like B as a unit isn't only if they're equal.
Because we know
Right.
it's always greater than or equal. Yeah,
Yeah.
because by what we have above, we know it's always greater than.
Right.
So, yeah. Now, pragmatically speaking, I much prefer to think about, when I got it, a multiplicative norm, right? Multiplicative norm, and going from the ring to the natural numbers has, what is the property of it? Well, that, first of all, its output is a natural number. But second of all, it's multiplicative in the sense that the norm of AB is equal to the norm of A times the norm of B. And furthermore, that pretty quickly tells you that the norm of A times 1 is the norm of A times the norm of 1, right? But that's also equal to the norm of A. This holds for all, right? So what does that say? Oh, and I'm sorry, there's something else. And also, the norm of A is not equal to 0 for A. For A not equal to 0. I mean, only n of 0 equals to 0 is usually part of the, if I remember right.
So that tells me, well, we know if the norm is 1, then it's a unit.
Right. So what I'm saying is that this says that the norm of 1 is just 1. So the multiplicative norm really satisfies our intuitive, and this is like your exercise 21 in the homework, right? Z adjoin the square root of D. You look at the norm built from the conjugate in there, like ZZ bar. They give us A squared plus DB squared or something like that. Now, of course, the norm of any unit will be 1 here, right? So you can find the units in the ring by looking for where the norm is 1. In my notes, I have a little argument that I probably would have trouble reproducing off the top of my head, because it involves inequalities which are perilous for me. See here. It would be fun to watch me teach reals. Where'd that stupid thing go to? I mean, this is, it must be 29. Yeah. So, let's see, it's a little bit, I say a norm n. You notice that I'm calling the divisor function a norm here, which is probably even more non-standard than other things we've looked at. But let's see here. So I think if you look at it, I think I got this definition from, I don't think I made this up, though. I think I copied this down out of yet another book. Anyway, you notice what's missing. This condition right here, although my brother said that is sometimes given and sometimes not given. Giving this, the main advantage to this is when you add that to the definition of Euclidean domain, it forces associates to have equal divisor functions. It forces all the units to, have, like you said, have delta of 1, just the same. But if I had a multiplicative norm, right, then, and which I have said is, well, I guess in Galilean, maybe he actually gives the same as Nicholson. And anyway, the larger point here is if I set the divisor function equal to the norm, you know, if you look at the divisor function of a and b if b is non-zero, then that means d of b is non-zero. So I can do this d of ab divided by, well, d of ab is d of a times d of b, right? So this would be d of ab over d of b. But that's a counting number. So this inequality is clear, right? Because this is like a fraction, and this is just keeping the numerator. So that inequality shows you that d of a is less than or equal to d of ab. My point is we can get, if you use the multiplicative norm equal to the delta, then it satisfies this condition. But you know, the multiplicative norm is a stronger thing. Not everything we work with has a multiplicative norm. I think the principal example of that would be what? What does have multiplicative norm? The algebraic integers, like the z adjoint square root of 5 or z adjoint square root of -2, those things. We got a nice multiplicative norm there. The integers themselves, absolute value function, gives us a multiplicative norm. But what doesn't have a multiplicative norm that we actually are interested in? Polynomials. The degree function is if I have f times g, is the degree of f times g the degree of f times the degree of g? It is not. The degree of f times g is the degree of f plus the degree of g. So the degree function is a non-multiplicative norm that we're interested in. I would love for us to only think about this, but it's just not. The example of polynomials forbids that specialization. Anyway, that said, I think the most interesting test questions are really, a lot of them are over in here, like your exercise 21 and related examples we've done in class, like, you know, this thing, right? This example 3.6.2, looking at irreducibility versus prime and so forth, yeah. Other questions?
Do we need to know, like, content and, like, primitive?
I don't think that matters too much. It's more important to know the theorems that are based on that. I don't know if I'm not sure I should rule that out. It's not a particularly difficult question. I mean, find the content of a polynomial. It's just I don't think it's interesting. I think you guys could do it. I just don't think it's interesting,
Okay.
personally. That's an interesting problem.
Which one are you talking about?
I don't know. Oh, did I say something?
So it was an interesting problem.
Oh, yeah. No. You guys have other questions? I could look at the Calculus 2 test and see how they did if you'd like to. No, that doesn't really help you, I guess, but
Yeah,
no. I don't know. The book we're using right now is so abysmal. It's hard for me to compare classes. I feel like this book is so, I don't know. I'm not happy with our book. Oh, no, Calc 2. Nicholson's great. I think Nicholson's an improvement over last year. How would you find all the ring homomorphisms going from Z4 to Z8?
Well, a ring homomorphism has to be equivalent. That's where I would start.
Here, I'll make it Z12. Why not? Or do we want to go the other way? I can't remember. So for this to be a ring homomorphism, what two things do we need? Yeah, we need to preserve addition. Yeah, and multiplication. And what did you say? Yep, and. Now, we had this item number, this bit right here, this means that it's a group homomorphism, right? From Z4 to Z12. And what were the terms and conditions on that? There we had a very overarching theorem about what the structure of that is. Yeah, I mean, we have a formula even. Phi of let's say x sub 4 has to be equal to mx sub 12, where m what? I don't think it's a relative. I think it's a divides condition.
It divides 4. No, that wouldn't make any sense.
M divides 12, you say?
I don't think it'd be that. I think it has to be 4 divides m. But then you wrote m first.
So I put you guys up a creed comp. 4 divides m, huh?
Is that right?
I don't remember. I'm asking you. You guys are taking the class. I'm just teaching it. What do you want me to think? I'm the source of all knowledge here? I mean, this is. I remember this. That it was problem. See, this is the annoying thing, as I don't. 196 in Nicholson.
Yeah, this is.
I remember the general story, but I don't just.
This isn't going to be what you're looking for.
Oh.
With the problem that we did, this talks about like m and relatively prime. Then we can. This was going to be going from Z12 to Z4. I guess we'll look at that.
Well, that phi, I think, is the well. That's the Euler phi function too, on corollary 2 on page 196. But I'm not saying this phi is the Euler phi function, obviously. In each case, well, this is kind of like exercise 3, section 3.4. Like, in each case, determine whether map theta is a ring homomorphism. Support your answer, right? So, gives us the map.
Oh, they have 4
Yeah. Great. Googly moogly.
Getting more comments on the YouTube videos?
Yowzers. No, that was just me. I think it. Come on. Next. Next. It's from Z to Zn. Well, that's great. Don't care about that. Nope, don't care about that one. Lovely. Don't care about it. Yep, that's the title. Nope, don't care. Words. More words. More words. Words. So many words. You know, apparently I say ring homomorphism a fair amount. Ah. Oh, but again, this is just going from Z to Zm. Dang it. See, I know that there's a problem on it. I can't remember which problem it was. I feel like it was like... Okay, where was it for you guys?
We had,
Find all the group homomorphisms?
well, yeah, and then we came up with that map, and we proved that we could come up with a general case.
So where was that? Mission what?
The
It
missions
would have been
before
like
test
4 or 5 or 6 maybe.
This is bad.
No, it's a written one, so it's the last problem. It's written by you, so it will be in the book. So it's not this one.
Oh, okay.
Yeah.
I gotcha.
Go up to like
I think this is still first time.
Right. But we should be looking first test, right?
Yeah, that's, well, that's
we
not
know?
all of our homomorphisms stuff, first test. Because 2 is, because that's the knowledge theorem.
should we have groups?
Yeah, first test had groups. She didn't have fancy groups. There were no factor groups at that point. You had not even, the word coset had not entered the scene. But we were talking about isomorphism and so forth. Well, it must be after that. I think it must, wrong topic. Might have been mission 5, maybe.
Oh, look at that.
Woohoo.
K divides M.
There we go.
So 12 divides.
See, I'm not supposed to have to remember this stuff because I wrote this to where, look, I have worked it all out for you here in the interest of you remembering it. You guys are younger than me. You're supposed to remember these things. It's understood that I'm an old person. I should forget things. But
It's 12 divides 4 M.
Dr. Vivian, very sorry, we don't memorize every single group.
why don't you memorize everything that happens in this course?
We try our best.
I'm very sorry.
I guess I'll get over it. Let's see here. What's the net result? I need to say it for myself so I can try to remember.
12 divides 4 M.
But if we're going from Zn to Zk,
Yeah,
I
so
need
K
that
divides MN.
K divides Mn.
Yeah.
So
Give us,
here we need,
so you can give us,
I need M,
So did you give it to Spectre?
I need, just a second here, I need K, I need, so, sorry guys, K equals what here? Or N equals 4. In my current language up there, K equals 12, right? And we need, what did I just say? K divides Mn. So that is 12 divides M times 4. So I was right about the divides by, but I was off about how it works. Obviously. So what would that, what are choices of M? Yeah, so we can, looks like we can do, you said M equals to 3. M equals to what? 6? 9, right? And of course, the ever popular 0. So there are just 4 group homomorphisms, right? Now, just because it's a group homomorphism doesn't mean it's a ring homomorphism. How do you decide which of these are ring homomorphisms? I mean, the candidates here are Phi sub naught, of x equal to 0, phi sub 1 of x, and here I probably should use my, x sub 4, right, is equal to x sub what? Oh, 3x, right? Sub 12. And phi 2, maybe I should number them more logically. Let's call that phi sub 3 and phi sub 6. That'd be easier for me to remember. So here we have x sub 4 maps to what? 6x, 12. And finally phi 9. These are your choices. So let me ask again, are any of these ring homomorphisms?
Well, we know that 3 isn't because phi of 1 would be 3.
Mm-hmm.
And then the same for
Right.
6 and 9.
So no, there are no ring homomorphisms. There may be RNG, maybe general ring homomorphisms. So let's loosen it a bit. Are there any general ring homomorphisms? So a general ring homomorphism, these two things. Or you might call it a RNG homomorphism, So drop the one condition. Can you find any homomorphisms of that nature?
Well, we know they all preserve addition.
Yeah, they by construction, if we trust the problem 50 argument, we've got addition. It's well defined at least.
So the test multiplication would be like, for 3, we have like x, y is equal to
Mhm.
3x, y.
So yeah, so it's a phi 3 of x times y, like you said,
Yeah.
is equal to, what is that? That's equal to, all right? And this is a sub 4, so this is 3xy sub what, 12?
Is not equal to 3x, 3y.
And then I think the kind of the easiest way to go here is to,
I just go backwards.
try to meet in the middle, and if you can show that you can't meet in the middle, then, that might help you see how to write a more,
And then you do 3 times 3 is 9. 9xy.
and 9xy12 is not equal to 3xy12, no.
Right. So then
To be more specific, you can take specific elements like x equals to 1, y equals to 2, or something like that. Ooh.
But from that, you can see that 6 should be right.
Yeah. For example, yeah. See, so phi sub 3 of 1 times 2 is, well, of course, good grief. This is what? Phi 3 times 1, so 12, and 2 times 1, good grief, 3 times 2. I'm sorry, guys. I'm having trouble organizing my work. My point is to look at one, show that this, anyway, to summarize what I want you to do. Once you've decided it's a falsehood, we should customarily provide a counterexample, right? They're not hard to find. So 3 is out. What about 6?
I think it should work. Wait. No, because you'll get 6xy, and then you'll get 36xy.
Which is automatically 0.
So, no.
Yeah, because, well, maybe 0 equals 0. Maybe it's okay. Well, I'm sorry, let me just...
But you would get 6xy for the other one.
Oh, and 6x, so this is, I got you. So that's 6xy, which is not necessarily 0, right?
Right.
Which is what we get from So pick anything you like, right? Like if you just do 1 times 1, for example, you can check that phi 6 of 1 times 1 is not equal to phi 6 of 1 times phi 6 of 1, because this is 6 and this is, which of course is 0. I'm not overly optimistic about 9 working either, right? 0 is there though. 0 is always a general ring homomorphism, right? So the larger story here, guys, is it's easy enough to figure out which ones are the additive homomorphisms, if you remember problem 50. But then to actually see which ones are ring homomorphism, there's no nice answer to it. You actually just have to go check case by case. Which is why it doesn't make a particularly good test question. Or does it? Sorry.
We're going over it right now, so you're not gonna get
I think Dr. Sprano commonly asks these, which makes me have, there's peer pressure on me for this question. So you think about that. But anyway, other questions, concerns, comments? Yep.
So when we're trying to find if something's irreducible or not, there's that rational roots theorem is one way. We were reading through, just trying to figure out like what is really catch-all best way to go about something.
What is the catch-all best way to decide whether or not something's irreducible?
Rational roots, is that always an option? But there's faster ways if you can just look at like Z2.
So if we're talking about polynomials over Zx, I mean integer polynomials, factorization of integer polynomials, then I personally usually fall back on either reduction mod prime to prove it's irreducible, right? Or Eisenstein I mean Eisenstein is my preferred method if I can do it, but certainly reduction mod an integer, that theorem is very important. And yeah, rational roots is also good. I mean, there are problems in the text which are based on rational roots, right?
Yeah.
In your homework also. So
But modify prime only works if it's degree 2 or 3, right?
Yeah, that's kind of what my question was. Like if we see something of a higher degree, we can't use that anymore, right? I thought that's what we discussed.
what?
Or like
Where are we?
do it for a higher degree.
Where is that section we're talking about? For 1? Sorry. Now, theorem 1 is the one I was talking about yesterday, which is that if you have a field and you have a polynomial over a field, right? That's a different context already. For polynomials over a field, it's irreducible if it has no root. Yeah. Okay, I finally understood theorem 1. So part 1 says if p is irreducible, then p has no root in f. I was like, well, but linears are polynomial. Linear polynomials are irreducible, and they have roots. But then I read the preamble to the theorem, and it says degree of p is greater than or equal to 2. See, that's important, because linear polynomials are irreducibles that have roots, right? But if the polynomial has degree 2 or greater, if it's irreducible, then it has no root. But the vice versa, showing it has no roots, implying irreducibility, that's only good if it's a cubic or a quadratic. For quartic, we have examples of quartic polynomials that have no zeros and yet are reducible, because they can be written as a product of irreducible quadratics or something. Yeah.
So like, we would have to use like sign on a.
Let's see here. So how about this one? Example 4. Example 4, show that p equals x cubed plus 3x squared plus x plus 2 is irreducible over Z5 on page 216. What's he do? He looks at 0, 1, 2, 3, 4. He shows that all of those are non-zero, and consequently p has no root in Z5 and so is irreducible. Well, I guess that's just a straightforward application of that. Sorry guys, that's not interesting. So page 217 is of course important, but I didn't really say it in class. Gauss's lemma. Theorem 6, f is reducible as a polynomial over the rationals if and only if it has no proper factorization in Zx. A proper factorization, so he's not, if you have like 2x plus 4 and I factor the 2 out, for him that's not a proper factorization. That's just, you have factored a 2 out. That doesn't really count. It's roughly his language. Fine. All right, eventually we get to a point in here. Example 8, he's got x to the 5th plus 2x squared plus 1, irreducible in Qx. Show that it's irreducible in Qx. So to do that, he looks at it in Zx. And he specifically looks at integer Diophantine equations and integer equations and shows that they have no solution.
Why couldn't we just have done the rational roots here, right, from the start there?
Rational roots.
Rational roots is on page 211. Oh, it has to be in Z with X. Rational roots theorem works in Z with X. I think that's what the theorem says.
Let's see here. I'm sorry, where is rational roots again?
211.
Yeah, you got to be really careful. There's strings attached to all these theorems, you know? Right, exactly. Rational roots applies to integer polynomials. And so we're in that other where we just were.
We're in Q.
Which example were we? We're
Example A, 219. Yeah, so he says we'll show that it has
example 8 and 219. Yeah, so it's irreducible in Qx, so that's right, it's the context. Yeah.
then he used rational roots.
Ah, very good.
He calls it a heavy handed method.
Yeah.
So he says it's less effective for polynomials and higher for
Let's see here. Then theorem 7, the modular irreducibility test, you have a non-zero polynomial with integer coefficients, and suppose you can find a prime p such that p does not divide the leading coefficient of f, such that the reduction of f mod p still has the same degree as f. And what else here? Oh, and you have to show that the reduction is irreducible, right? Yeah. Now, you're right. This is only most nice when the polynomial has degree. Okay, first of all, if p is a prime, Zp is a field. So the theorem I stated before about polynomials over a field applies here. So certainly if it has degree 2 or 3, then we can just plug in the finite number of elements in this finite